Hi, my name is Harlinda Kaur, daughter of Amrit Pal Singh. My matrix card number is 01DEE24F1120. So today we will be talking about bipolar junction transistors, which are also known as BJTs. So firstly, I would like to introduce you to the bipolar junction transistor. A bipolar junction transistor is a three-layer semiconductor device that plays a critical role in electronics as both an amplifier and a switch. It consists of three regions, which is the emitter, base, and collector, which is formed by sandwiching two p-n junctions together. BJTs are called bipolar because they conduct current using both electrons and holes as charging carriers. Unlike unipolar devices like MOSFETs that use only one type of carrier. BJTs are significant in electronics because they can amplify small signals, for example in audio amplifiers, or act as switches in digital circuits, as for an example in logic gates. They were a cornerstone of early transistor technology and remain widely used in applications requiring high current gain, such as in power amplifiers, RF circuits, and analog systems. Despite the rise of MOSFETs in modern integrated circuits, BJTs are still preferred in certain scenarios due to their high current handling capability and linear amplification properties. The objective of Experiment 3 is to explore the fundamental aspects of BJTs by examining the three terminals, which are the base, collector, and emitter, and their roles, the two main types of BJTs, which are NPN and PNP, and their operational differences, the materials used to manufacture BJTs, such as silicon and germanium, and their impact on performance. This experiment aims to provide hands-on understanding on how BJTs function in circuits, how to identify their types, and why material choice matters. Secondly, identifying and explaining the three BJT terminals, which are the base, collector, and emitter. A BJT has three terminals, each with a specific role. The first is the base. The base is the control terminal. It's a thin, lightly doped layer that regulates the current flow between the other two terminals. A small current applied to the base can control a much larger current flowing through the transistor. The second is the collector. The collector is the terminal where the majority of the current enters in an NPN or exits in a PNP transistor. It's moderately doped and collects charge carriers coming from the emitter. Third is the emitter. The emitter is the terminal where the majority of the current exits in an NPN or enters in a PNP. It's heavily doped to supply a large number of charge carriers for current flow. The BJT operates by controlling the current flow between the collector and emitter through the base. A small current injected into the base, called the base current IB, modulates a much larger current flowing from the collector to the emitter, called as the collector current IC. The emitter emits charge carriers, electrons in NPN and holes in PNP towards the base. The base, being thin, allows most of these carriers to pass through the collector. The relationship between the currents is governed by the current gain, beta, where IC equals to beta times by IB. Typically, beta ranges from 20 to 1000, meaning a small base current can control a significantly larger collector current. Next, let's describe the current flow in both NPN and PNP transistors. In a NPN transistor, the emitter is N-type, the base is P-type, and the collector is N-type. When the base emitter junction is forward biased, positive voltage on the base relative to the emitter, electrons flow from the emitter into the base. The thin base allows most of these electrons to be swept into the collector, creating a large collector to emitter current. The current directions are IE flows out to the emitter IB, flows into the base IC, flows into the collector. In a PNP transistor, the emitter is P-type, the base is N-type, and the collector is P-type. Here, the base emitter junction is forward biased by applying a negative voltage on the base relative to the emitter. Holes flow from the emitter to the base, and most pass through the collector, creating a current from emitter to collector. The current directions are reversed compared to NPN, in which IE flows into the emitter, IB flows out of the base, and IC flows out of the collector. Thirdly, BJTs come into configurations based on the arrangement of their semiconductor layers. NPN transistor consists of two N-type layers, which are the emitter and collector, sandwiching a P-type base. It's the more common type because electrons, which are the majority carriers in N-type material, move faster than holes, leading to better performance in many applications. Whereas the PNP transistor consists of two P-type layers, which are the emitter and collector, sandwiching an N-type base. It's less common but useful in specific circuits such as complementary symmetry amplifiers, for example, push-pull amplifiers. Next, we will be comparing their differences in terms of current flow direction and biasing conditions. The current flow direction in an NPN transistor, the current flows from the collector to the emitter. Electrons move from the emitter to the collector, so conventional current, which is opposite to electron flow, is from collector to emitter. In an PNP transistor, the current flows from the emitter to the collector. Holes move from the emitter to the collector, so conventional currents aligns with this direction. In biasing conditions, for an NPN transistor to operate in the active region, for amplification, the base emitter junction must be forward biased. Base is approximately 0.7 volt higher than the emitter for silicon BJTs, and the collector base junction must be reverse biased. Collector is at a higher voltage than the base, typically VCE more than 0 and VBE approximately 0.7 volt. For a PNP transistor, the base emitter junction is forward biased by making the base approximately 0.7 voltage lower than the emitter, and the collector base junction is reverse biased. Collector is at a lower voltage than the base. Here, VEC is more than 0 volt and VEB is approximately 0.7 volt. Fourthly, we'll be demonstrating how to identify an NPN versus PNP transistor using circuit symbols and testing methods, for example using a multimeter. Firstly, the circuit symbols. The symbol for an NPN transistor shows an arrow on the emitter pointing upwards, indicating the direction of conventional current flow from collector to emitter. The symbol for a PNP transistor has the arrow on the emitter pointing inwards, indicating current flow from emitter to collector. Multimeter in diode test mode can identify whether a transistor is NPN or PNP by testing the P-N junctions. The steps are: firstly, set the multimeter to diode mode. Secondly, identify the base. Test pairs of pins to find the base. For an NPN, the base to emitter and base to collector junctions will show a voltage drop of 0.7 volt for silicon when the positive probe is on the base and the negative probe is on the emitter of the collector. For a PNP, the drop occurs when the negative probe is on the base and the positive probe is on the emitter or collector. Number 3, determine NPN or PNP. If the base is P-type, positive probe on base shows a drop, it's a NPN. If the base is N-type, negative probe on base shows a drop, it's a PNP. Fourthly, confirm terminals. Once the base is identified, test the remaining two pins, collector and emitter. The collector-emitter path should not conduct in either direction without base current. Next, we will be discussing the materials used to make BJTs such as silicon and germanium. BJTs are made from semiconductor materials, primarily silicon. The most widely used material for modern BJTs, silicon has a band gap of 1.12 eV, making it suitable for a wide range of temperatures and applications. Germanium, used in early transistors, example in the 1950s, germanium has a smaller band gap of 0.67 eV, which makes it more conductive but also more sensitive to temperature changes. Other materials like gallium arsenide are used in specialized high-frequency BJTs, example in RF applications, but silicon dominates due to its cost-effectiveness and reliability. Silicon is preferred over germanium for several reasons. The first is thermal stability. Silicon can operate at higher temperatures up to 150 degrees Celsius without significant leakage current, whereas germanium starts to fail above 75 degrees Celsius due to its smaller band gap, which leads to increased thermal generation of carriers. Second is electrical properties. Silicon has a higher breakdown voltage and lower leakage current, making it more reliable in high voltage application. Its oxide forms a stable insulating layer, which is crucial for manufacturing processes like passivation and integrated circuits. Third is availability and cost. Silicon is abundant, which means the second most common element in the Earth's crust and cheaper to process than germanium. The semiconductor industry has optimized silicon fabrication techniques over decades. Fourth is the performance. Silicon BJTs have a higher current gain and better switching characteristics in most applications compared to germanium. Germanium BJTs, while historically significant, are now niche, used in some audio applications for their unique sound characteristics due to lower turn-on voltage, which is 0.3 voltage versus 0.7 voltage for silicon. Lastly, to summarize everything, Experiment 3 reveals that BJTs have three terminals, which is the base, collector, and emitter, with the base controlling the current flow between collector and emitter. Second is there are two types of BJTs. The first is NPN, in which current flows from collector to emitter, and PNP, in which current flows from emitter to collector, distinguished by their biasing and current flow directions. Thirdly, silicon is the dominant material for BJTs due to its thermal stability, electrical properties, and cost effectiveness compared to germanium. Understanding BJTs is crucial for circuit design because, firstly, terminals. Knowing the roles of the base, collector, and emitter allows designers to properly bias the transistor for amplification or switching. Incorrect biasing can lead to malfunction or damage. Secondly, types. Choosing between NPN and PNP affects circuit topology. For example, NPN transistors are often used in common emitter amplifiers, while PNP transistors are used in complementary circuits like push-pull amplifiers. Thirdly, materials. Material choice impacts performance. Silicon BJTs are reliable for most applications, but in specialized cases, for example, high frequency or vintage audio, germanium or other materials might be preferred. BJTs are foundational to analog and mixed signal circuits, and their proper use ensures efficient, reliable designs.